So visual recognition is a problem that we take for granted because it seems so natural. I often say in my talks that I sort of ask, my mom will ask me what I do, and I say I study how we see, and she says, well, we just see. It's obvious, it's easy, we do it. And it's so easy that we take it for granted. But it turns out to be quite computationally complex, and one of the things that has surprised us in our work there is that many of the workers in the field thought that this would be a problem that would require many processing loops, recurrent neural networks to solve, where information would have to be propagated up, edges would have to be computed, eventually you build up an object, you might have to have circular feedback loops to be able to compute complicated structures. It turns out that you're able to compute something that very much matches human perception and neural activity by doing what's essentially called feed-forward processing, stacked sets of nonlinear filters that are essentially just pushing information forward through a series of layers that look like the visual areas we see in the brain. It's a very sort of, on its face, simple form of computation, yet it's activated in parallel with appropriate nonlinearities, appropriate slight changes in the processing that are learned either through evolution or development, we're not sure yet. But that simple form of final computation buys you a lot of processing power. And it was thought that that would not be the way it works, but a close examination of the brain shows that the times at which you're able to compute are so fast, and the models are now consistent with this idea that you compute this almost in a natural, automatic way, that the visual system is set up to take any image data and make the content explicit in a very natural, or very quick feed-forward way, rather than having to build symbolic logic or complicated structures that require recurrent loops of processing, which was how computer vision had thought about this problem early on. And the brain teaches us, it's done in this way that is very effortless and almost very automatic, which resonates with how we feel about it, that it feels quite easy and automatic. And it's because we come somehow pre-built, at least after development, to have such a very fast, automatic processing system. And that was a shock to many workers in the field, was maybe less of a shock to those of us who were looking more directly at the brain, but is now really the standard model of how vision should be done even in machine systems. Let me back up and give you the big picture. So the brain has a sensor at the front called the retina that's like a camera. That camera takes the data, copies the image of the world, passes it to a series of visual brain areas down what's called the ventral visual stream to a high-level brain area which is called infratemporal cortex. That area has patterns of neural firing that we think are what underlie each of our perceptions about what's out there in the world. So the brain transforms the data to a new pattern of neural activity that's not a photograph. It looks nothing like a photograph. It's some distributed pattern of neural activity in this place called infratemporal cortex, which was previously a quite mysterious part of the brain. So our lab works on two facets that relate to infratemporal cortex. One is, how do those neural patterns relate to the perception? I said they relate, but exactly quantitatively, how do they do that? And so we use devices, we put in things like LED arrays or single electrodes to try to activate individual groups of neurons or patterns of neurons to essentially inject percepts, we hope, by manipulating neural activity at this high level of infratemporal cortex to cause an animal subject to, say, perceive a face, not perceive a face. For example, perceive a car, not perceive a car. And those are the building blocks, we think, to being able to have similar devices, maybe not exactly the kind that we use, but the understanding could be used to enable similar devices to perhaps be used in human subjects to replace lost vision, where they've lost all that transform between the eye and the infratemporal cortex. So that's one aspect of work. But as you can see, even if we can inject those percepts, we need to understand how the brain takes the visual image and transforms it through all these pathways up to IT cortex, up to those mysterious patterns of activity. We call that neural encoding. That's studied by building computational models that have a similar layered structure that take as their input sensor data, an image, and try to reproduce the patterns that we measure, not only at the top level at IT cortex, but at the intermediate levels that feed into IT cortex. And we try to model all of that as our building of an understanding of the system. And you can see from a neuroscience sort of view, or really a cognitive neuroscience point of view, if we can do that, we'll have what I call an end-to-end understanding, from the image all the way through the brain, all the way to the perceptual variables of interest for this particular problem domain. And you see there's two ways to think about how our work applies. One is direct percept injection. The other has to do with algorithms that process information in a similar way to our own brain.